Hey, what time did you pick? What time did you want to go over the setup? No. Yeah, I mean, like, I don't know what time I'm gonna finish, so. Oh, okay, okay, I get it. Uh, I mean, if you're okay with staying here, we could plug your computer in here and how much of it is like specific to your project versus just would be generally applicable to everyone?
I mean, for me, that would be pretty, the boundary for me is pretty tight because I just don't want to go too much on my project. My plan is just try to get pictures taken. For example, just for a small item or something, take several pictures,
Hmm.
stitching them together, and let that code run with the pictures and finally get the 3D models. So I
I
think
mean,
for
from what I understood, what you wanted help with was just like setting everything up, right?
yeah,
The GPU access and
setting
environment.
everything up and also run because it looks like some of the packages and functions I haven't used it before.
Okay.
Yeah, I just want to make sure I understand what it's for.
Ah, okay, okay.
Because
Um,
they already built up the code for everything. So
hmm.
if I it's kind of like it's like it's no difference from dropping the pictures into the software and then let the software do the work.
Hmm.
Yeah.
Okay. So, in that case, I'm guessing you would prefer doing it over Zoom because that would give you the ability to record it. Yeah, we can go over it at one and over Zoom is fine.
Okay, 1 o'clock.
Yeah.
Okay, that works.
All right.
I'll just wait. You or
I'll I'll send you an invite once I get back to my office after here. Um, if people ask me stuff after class, then that might take a while because I
yeah,
typically stay till like 12:30 or whatever. Okay, yeah. Oh, one general housekeeping thing. I posted a poll on Piazza asking about how many of you need CCR access, with the emphasis on need because it's kind of a pain to set up. And it's also not very, there's a bit of a learning curve. So if you're able to get away with uh, anything other than CCR, that is what I would recommend. But if not, then please indicate that you do need CCR access because I have to request resources accordingly um, based on what I think the like if it's 5 students or well, I'll have to request storage and compute according to that. And that is also a bit of an involved process, and I want to get started with that sooner rather than later. Um, this is kind of what I would have to go through basically. I have this project set up for the class, and I'll have to add your accounts to the project and also request an allocation according to um, what we think the estimate for compute necessity is. And the poll is up here. That's what it looks like. So if you think you're going to need CCR, please let me know so I can add you to the project and get all of that set up. Okay. How do we feel about everything that we've covered so far? Are we comfortable with what goes on under the hood a little bit? Feature maps and getting stuff using it? Because what we're talking about today is continuing with that line of reasoning and thinking about what goes on inside. Um, I do intend to make another Jupyter notebook with a whole bunch of visualizations to sort of walk you through the whole process of what happens within a network. Um, I was aiming to do that yesterday, but I ended up going over your refined proposals instead because I feel like that could use feedback sooner. And the demo, I'll work on that over the weekend and see what I can come up with for next week. So where we left off last class, just a really quick recap of the things that we talked about. Segmentation was the problem that we were trying to solve. The format in which we store that information is something like that, which we call the segmentation mask. Each pixel in that would have a class label associated with it. And basically what you have is for each class, you'd have one of these maps as one channel corresponding to that class. And wherever a pixel is associated with that class, you'll find a positive value for that pixel in the mask. And using this, we're able to isolate where objects of a certain class are in terms of just pixel locations. And the issue that we saw with doing it that way, where we're just assigning class labels for each pixel, was that when you have objects of the same class that sort of overlap or are very close to each other, you can't tell apart instances of that class. And that is the problem that we will begin to solve now. So for object detection, we've probably already seen outputs like this, but this is the idea. This is what we want. So here, what information do we have? Throw words out. What do we see? Okay. Colors, edges of, are you talking about the boxes or just in terms of what's in the image? So, sorry, could you say that again? Okay, fair. Um, yeah, whatever, even when we're doing segmentation classification, that is definitely part of the set of cues that the model would pick up on. I'm looking more specifically for, I don't know, anything that jumps out about the boxes. What do the boxes tell us? Yes, location is one. Description. Description is the class, and there's also a third aspect. Yeah, where she said they're unique. And what I'm taking that to mean is that we're able to tell apart instances of the same class. So in addition to knowing that there's an object of class person at a location, we're also able to the location and class information combined lets us separate instances of classes. And so far, we have the ability to get classes associated with pixels, and location has been a bit of a challenge since we do that naively. And predict classes for each pixel and then let the chips fall where they may and sort of decide location information based on that. One of the key ideas that object detection is informed by is something we've already looked at before, which was the deformable parts model, where we extracted features for the entire image. And additionally, we were also considering parts of the bigger class object that we cared about and the relationships of the parts with respect to each other. So that informs what the overall class feature map should look like based on its components. And we would take something like this and do like the sliding window thing that we saw with the hog feature extraction and applying that to all parts of the image, looking at what the responses are. If you find a region that has a high response, then odds of there being an object over there were high. And the downside for that, if you would recall, is that we had to run it a whole bunch of times. So we're chopping up the image into little windows, running it. It's a lot of computation. So one of the ideas that I had on my slides for last class was that the difference between doing, say, classification or object detection, segmentation, all of that is a question of how you formulate the problem. So at the end of the day, what we're doing is we're using a surrogate function to sort of hint at what the right predictions would look like. And we use an optimizer to minimize the error between our predictions and what it actually should be. So we care about how to represent the ground truth, how to represent the entire problem in a way that you can minimize errors. So we'll be talking about those things. The first thing to understand is that this is a bit different from classification or segmentation, where you have discrete values that you can directly compare. When it's a box, you need to represent its location somehow. And you could have a box that's a lot bigger than what the ground truth is. You could have something that's a lot smaller, something that's far away. So in addition to shape, we also care about location. And the way the quality of bounding boxes is evaluated is by assessing how well it overlaps with what the ground truth is. So if, let's say, the red one's the ground truth, where it actually should be, and the green is what we predicted, the intersection of both of those is that region in the center over there that's highlighted. Terms from set theory, intersection and union, I'm sure we're familiar. Yeah, you can sign in. I'll put it away after you're done. Okay, where was I? Yeah, intersection. So we all know what intersection and union are, right? We're familiar? Okay. So you take the region that it got right versus the total regions that both of them span, and then just look at the ratio of that, and that gives you a sense of how well it overlaps. Because if your intersection is, if they're perfectly overlapped, then both of these are going to be equal, and you get a ratio of 1. And if there's no intersection whatsoever, then that's 0. So 0.5 is what we usually use as the threshold. And using that, we're able to say whether it's correct or not. So there's that final thresholding step after we calculate the intersection over union, or it's also shorthand called IOU usually. Apart from that, there's a few other metrics we care about. You've probably seen things like the F1 score, and precision and recall are components of that we use to assess the correctness of the just how many of them we got right. That we can get some sense of how well the model is doing using recall and precision. Generally, most predictions, you would find that they're low precision and you're getting high recall, which would indicate that the discriminative abilities leaves something to be desired for, and that the model is sort of memorizing stuff rather than inferring from what you're throwing at it. This is a bit less intuitive, but you basically, over here, we assumed a threshold of 0.5. What happens over here is you vary the threshold from whatever range, 0 to 1. And at each threshold, you plot the relationship between precision and recall. And the idea is that a model that does well would have a larger area under the precision recall curve. And this is kind of unintuitive. So further detail and intuition, I would just, once I put up the demo that I'm talking about, either that or I'm leaning towards having you guys implement mask RCNN, which is where we're going to end today, and object detection algorithm. You could look into it as part of that and just play around with the thresholds and see if any of that makes intuitive sense, if you're able to tease out what happens under the hood. We touched on the Pascal VOC dataset that had segmentation masks as ground truth, which was used to train a bunch of segmentation models. It had 20 classes, 11,000 odd images, almost triple the annotations. DPM is deformable parts models that we've talked about a bunch of times before. And that didn't really do all that great. So this was the state of the art, more or less, before neural networks were adopted for this sort of thing. So to adapt our existing CNN formulation that we're familiar with, which we've used for classification, one of the first approaches was called RCNN, where the R has to do with regions. And regions, why that's in the title is because the fundamental, the heart of the approach involved predicting candidate regions that might contain an object. So instead of applying something like our deformable parts model to an image for each and every possible window in the image, we're constraining the set of regions that we analyze by narrowing it down a little bit. and proposing candidate object regions, and then those are obviously going to be of different shapes because your objects are not going to be the same size always. But one of the caveats with the way we have built our model is that it expects a fixed size input every time, so that gets squished to whatever shape the model expects. And it gets passed into the CNN, which extracts a bunch of features and then classifies each of those regions. So for a very busy image, you're going to get a lot of these region proposals, and then we take each of those and throw it into a CNN and classify it to predict whether it's what object it might be. So that approach that they took to do the region proposals is somewhat similar to what we saw with the example with the flower initially, where we did k-means based on pixel colors to sort of group them together, giving something like that, which you could also think of as a superpixel representation. And the way these masks are built is just by going off of the pixel values. So you have a blue region that's close to each other, similar pixel values, and those form a group. And these can then further be refined using the same grouping process iteratively until you basically get to control the granularity of proposals that you get. So the less detailed your sort of superpixel segmentation mask is, the fewer candidate proposal boxes you get. And then that's fewer times that you have to run a whole CNN to predict what class is in it. That would take about 20 seconds per image. So in addition to classifying what region, what class each proposed region is, we also care about getting the boxes right. So there was some additional logic to refine the predicted bounding boxes. And since we have a whole bunch of these, we only want to keep the best ones, so we do non-maximum suppression the way we did for during the edge detection pipeline. And there was also some additional approaches that some people took, where they would use additional networks to sort of inform patterns of what is adjacent to what typically, kind of like the deformable parts, where we bias the model with this assumption that parts are usually related to each other, and the odds of finding a hand around an arm are higher than normal. So all in all, there's a lot going on. A lot of forward passes, and it does better than the previous best, which was deformable parts. But up until this point, nobody really paid a lot of attention to trying to do it fast. They just cared about getting it right, which was fine for them. And then Dr. Redmond, whose slides I'm using for good reason, he's the one who came up with YOLO. And I figured when we when we have it coming straight from the source, I might as well use that because this has been one of the most influential models, I'd say in the past 5-10 years. And even if you haven't worked with it directly, I feel like most people have at least seen this sort of output. So it's permeated through like general social consciousness also to some degree. The problem with what we were doing in RCNN was that we had a lot of proposals and we were running predictions for each of those regions of interest. So how can we simplify the process? YOLO stands for you only look once. And the way Dr. Redmond got around the whole multiple in pass predictions for each ROI thing was to sort of include the region proposal logic into it and jointly predict all of the things in one single pass. So there's only one forward pass being made. What happened? My PowerPoint died. It's gonna take a second, sorry. Oh, okay, there we go. Okay, I'll leave the audio on, whatever. Okay, no, we're not doing that. That is Dr. Redmond. And this is a lot faster than 20 seconds per image, and we're getting all of these bounding boxes. It's a bit sped up, I guess, but it does a reasonably good job. And this, I believe, was from the first iteration of the model. And I think Dr. Redmond wrote 3 of the YOLO papers. And then after that, people just took the name YOLO and ran with it. And a lot of the newer ones don't really have anything to do with him. So how did he change the process? That there was some key insight that everyone else missed, that by changing the way the problem was formulated and what we were looking for, what is predicted, we're able to speed up the whole process several times. So how YOLO works is you have an image, you break it up into a bunch of smaller parts, even grid. And for each cell, we're predicting the probability that that cell comes from an object. So you've seen those CAPTCHAs with the big image that is broken down into tiles, and then they ask you to find like a traffic signal or a bicycle or something. And you have to select all of the parts that contain it, right? Which is this format, pretty much. Where what we're telling them when we're doing the CAPTCHA is that there's an object of class bicycle in this cell of the grid that makes up the larger image. So this is what we're telling it, probability of 1 when we do that. And then here we're trying to estimate the probability that this comes from a larger region that contains an object. In addition to that, oh, I missed that. That's on me. That there should have been a bounding box like this one over here. In addition to predicting just the class probability for that cell, we also predict what bounding box it must have come from. So something like that. And then we do that for every cell in the grid. Now, some of these boxes are thicker than the others. Does anyone want to guess why? Yeah, yeah. So we're predicting the probability that it comes from an object. We're also predicting a box to go with it. Some of these probabilities are going to be between 0 to 1. And that's just a way to sort of encode how confident the model is about each bounding box that it predicts. And that correlates with the probability that it predicts. Now, we also want to know classes. So in addition to the things we've predicted so far, which is probability of there being an object, a potential region from where it must have come from, we also want to know what the object is. So class probabilities is also something that is predicted. And so at this point, we have a few channels worth of predictions and ground truth that we would like to compare and optimize the loss function. So for that, we care about representation. Now, visually, this is simple to interpret because if you have a legend over here that tells you which color is what class, then this contains all of the information that we've covered so far. A lot of boxes. I'll get to the representation point that I was trying to sort of segue into, but this is really busy. We only want the best ones. So using the probability information that we have, we only keep the best ones. And that gives us this. So doing all of this in one step would require a representation that allows us to have all of that information in a single output. This is one of the other big innovations, I guess. So our labels and our representation has increased a fair bit in complexity, but the idea is pretty simple. So one of the challenges is that we can have multiple boxes per image. So in that case, you can just stack these, but each predicted bounding box along with class is stored in the form of a tensor where the first channel is the probability mask that we saw from the first step. So a grid of probabilities, and the coordinates of the corners of the bounding box. This would be top left, I believe, and then you add width and height to those. So if you think about what values are in there, those would all be sort of correlated channel-wise. If you go along the channel axis, you will find height and width in the same spot for a given x, y, and also probability. And then for however many over here, it's 6 to 25th, because this was for Pascal VOC, which had 20 classes. If you have more classes than 1,000 classes, you'd have 1,000 more channels over here. So probability of the object being a cat, object being a bird, whatever. This is now a format that we're able to both predict and compare with our ground truth. Now, since there's all of these components that we're predicting at the same time, comparing them, you can't just sort of mean squared error the entire 3D tensor directly, because each channel means something different. They represent different things. And we want to incorporate that understanding that they're different into the way we optimize the model. So there's three components to the loss function. There's confidence error that we look at, there's localization error, and there's classification error. And how much each of those contribute to the total loss is tunable with these alpha parameters. For confidence, that's a question that since it's either an object or not an object in that cell of the grid, that becomes a binary classification problem, and we apply binary cross entropy. For localization, we look at the root mean square error of the predicted coordinates and heights and widths. And for the actual classification, well, it's multi-class cross entropy, or you can also do them for each class as one versus all the other classes. RCNN, one of the major bottleneck was that for each image, there were candidate region proposals. And we were applying a convolutional neural network to each of those regions, and then doing bounding box regression to refine the predicted boxes and also use an SVM to classify. So there's a bunch of things that we would like to swap out and change the sequence of operations also to make things faster. So then they built fast RCNN. And the intuition is kind of similar. So instead of extracting features and doing region proposal using those, which then each go into a separate network, we use a convolutional neural network directly to get a feature map, and then propose regions from that. And there was this new step called ROI pooling that was added in there to sort of average all of the information from candidate ROIs and then throw that into a fully connected layer. So Con5 is the fifth convolutional layer's output from, I believe this would be ResNet, but I'm not certain about that. I would have to actually, I would encourage you guys to, I've linked to whatever papers and stuff are relevant on each side. So for inner workings, they're always there if you're curious. And then the class predictions and refining our bounding box coordinates and heights and widths, all of that at the end. ROI pooling also serves the purpose of getting our inputs for subsequent layers into a standard format that the downstream layers would expect. And the way that works, ROI pooling is naive in how it samples regions. ROI align is something that was introduced after that, which is better. And ROI pooling is not really used anymore. So ROI aligning is what we're going to talk about. The whole grid, you can assume that to be some feature map from which you want to sample an ROI and regularize it into the expected shape. So the way that's done is by dividing it into smaller regions. So similar to how you would max pool or whatever, it's going to end up as a weighted sum, but the regions are sampled using something like bilinear interpolation. We're doing just more than one value for each region within the bounding box. So there's multiple pixels that each sub-region within the region of interest span, and we want all of those to contribute to the value. So we use interpolation to get sort of one uniform value for each subgrid, and then pool over that. The major things that have changed is that we're not running multiple CNN forward passes for each proposed region. But we also have a way to regularize our inputs to the desired shape as part of the network itself. And there's this part is freezed once you're able to get good feature maps. So the only thing that would need to be tuned really is the final layer. But this now leaves us to the bottleneck in fast RCNN, because there's still one component that isn't part of the network, and that's the region proposal part. Because up until this point, we're still doing selective search on the feature maps to get our proposed regions and then do all of this stuff. There's a theme to how these models are being improved. If you've been able to pick up on what that sort of approach has been up until this point, you should be able to guess what they do to solve the region proposal part. Anyone feeling bold? Another network. So region proposal using selective search was again something that someone came up with the idea being that, well, similar pixels, you could group them together and that might be indicative of there being an object. Instead of that, how about we just let another subnetwork figure out what should be a good candidate region, so then you don't have to think about how to quantify what might or might not be an object. Just train another arm of the network to do that for you. Keep everything else. We still have our feature maps, we're getting region proposals, and we're pooling them and applying our classifier. So that is fast and accurate. In here somewhere, let's see, faster RCNN using a ResNet backbone, which was pre-trained on Pascal VOC and Coco, which I'll talk about in a second. We have this is average precision for each class and for all classes overall. There's a few more methods that tweak a few things here and there. This one's using a REST Next backbone instead of the vanilla ResNet. This one's a fully convolutional, so it doesn't have a fully connected linear layer at the end, but instead it has a 1D convolution at the end, which effectively does the same thing, but with the advantage of weight sharing that you get from using convolution. So at this point, it's starting to resemble what was going on with ImageNet, where everyone's fighting for marginal improvements, diminishing returns. So we need more data. And this is something that Microsoft came up with initially, but then I'm not clear on what exactly happened, but they didn't want to be associated with it for some copyright, whatever reasons. At least that's what Dr. Redman had in his slides. And this has a lot more classes, a lot more images, and what's different here, what is different here relative to the Pascal images that we saw? This lets us do one thing we weren't able to do before. Right, yeah. So these are all objects of the same class, but we have instance level labels for each mask. That lets us fuse both what we're able to do with this and with object detection, where segmentation, we are representing our ground truth masks with pixel level labels, but only had class information. This has bounding box labels, so it's not a very exact outline of the object, but it localizes it really well and also tells you what class, and that it's distinct from another region, because you can have more than one, there's that region of overlap. There's two cars within the bigger box, essentially. We put them together. Coco enabled that with its instance level masks that are saved as pixel level labels. And then to solve that, to use that, Mask RCNN came along, which I believe was made by Facebook, but that is also something that I have to look up. It's been a while since I've fiddled with these directly, but here we have our bounding boxes, which it predicts, similar to YOLO and faster RCNN. But in addition to that, we're also predicting pixel level class labels. So that gives you an exact mask and the bounding box. The way it works, there's a separate subnetwork that does the mask prediction, and really there's the feature extraction part, which leads into the class prediction part and the bounding box prediction part. So it's got two arms that are predicting both formats. One with the 3D tensor containing box information like we saw for YOLO, and there's also the flat direct mapped representation where there's channels corresponding to classes and a map. And yeah, that covers object detection for now. Beyond that, well, I do have a couple demos, but I I feel like this would probably confuse you guys more than it would clear things up. So I want to add more visuals in here. Yeah, I guess I'll stop here. And then I haven't decided yet, but either I'm leaning towards just dedicating all of next class to going over code to put all of these things in context. Just quick show of hands, would you guys want that? One whole lecture just on demonstrating all of the things that we've talked about? Okay. I'll work on that over the weekend, try to make it as visual as possible. Apart from that, yeah, CCR, I'm done with content. This is just a couple of things that I wanted to put out there, basically. I posted a poll about CCR access. I was talking about this earlier in class, so for people who got here later, don't miss that. If you believe you're you have no alternative to using CCR, then hit yes on there, and I'll get started on requesting allocation for that and getting you access. I personally haven't used CCR before, so if you run into trouble, then we're going to be figuring it out together. Just be warned that I'm also not familiar, but I will do everything I can to figure out whatever problem you may run into with that. Yeah, and I I hate having to do this, honestly, and I don't want to like come in between you guys' friendships and whatnot, but going forward, since I don't tell you guys when quizzes are, I want you to assume that there could be a quiz whenever. And if you could leave a seat, that there's plenty of room here, and you can still hang out and be friends and whatnot after class. Yeah, and like closer to the front. Because if not, then if you're all like grouped together, then I have a hard time isolating if someone is doing something they shouldn't, and then the only choice I'd be left with is to give an entire cluster zeros on a quiz, and I don't want to do that. So this is the best solution I could think of where we meet halfway. Yeah, just next class onwards, if all of you could come up closer, that would help it be more engaging for me also, so I can gauge better how everyone feels. It's okay if you're not fully awake. That doesn't really bother me. I've been a student too, and this is early for like grad student schedules, I guess. I used to wake up around noon during my master's, and I only picked classes that were later in the day. So um, yeah, this is on you guys also for picking a class that was scheduled earlier. That's about it. If you guys have questions, oh, I gave out feedback on the refined proposals that I got. Most of them I had no complaints about. Seems like you guys are all on the right track, making good progress. And I also posted on Piazza, just that wasn't like harsh criticism or anything, just a couple of pointers to work towards for the final submission, because some of the ideas that you guys are working on, I think, are unique enough that if you put a bit more elbow grease into it, you could publish something off of that. And um, I would love to see that happen. There's really cool ideas. Um, yeah, so doing stuff the right way and being like thorough with your lines of inquiry and just understanding what you're doing is essential for that, to sort of increase the likelihood of that outcome of having something publishable. Uh, yeah, that's it. I can take questions up here. Yeah. All right. This one? This? So initially, starting out, you would just when the model doesn't know anything, just a random box that. Uh, so the format is x and y coordinates, height and width in the tensor representation. So you just predict random values for x and y, top left corner and height and width, and then
Like previous algorithms, and why is it fast? That's my question. I don't get like how it became so fast.
it became fast. So before that, what was, sorry. Maybe grab a seat for a while. I want to finish answering this.
Yeah, I can ask you to bring that to me.
Okay, yeah, that works.
It's about like the image stitching.
Okay, yeah. All right. Okay, so here, region proposals that we were getting were based on this selective search, right? And then you run a CNN, you run a classifier on each proposed region. So that takes a long time. Right, yeah. Because it's not just the quality of the bounding box that's being evaluated, but you're also like the order is inverted, right? You're okay in YOLO.
So this what happens. Like if this region has like a probability of so do we make a bounding box for car here?
Yeah, you just your best guess of what the bounding box would have looked like, because if your feature extraction and stuff is pre-trained on something like, let's say, ImageNet. I'm not talking about YOLO, but you have some idea of where that feature map would be found and what the feature map around it would look like. That's when you already know. So in this case, if you're starting from scratch, you just predict some guess of top left, and all of this is predicted simultaneously. So no, not this is the start. So you also have all of these, right? These don't really correspond to any actual object. That's just a bounding box that was guessed. And
So what I
For-
understand right now is NU, finally creating the smaller boxes is being taken and each are given a classification
yeah,
for you.
yeah, but they're not all run separately. The the final this uh, is the same size as your number of grids. So this grid, what is this? 7 by 7. Um, each channel here will also be the same size. So that particular block is the one that had the red high probability one. That gives you the probability of objects for the entire image in one go. And you're also, all of this whole tensor is predicted in one forward pass. So these channels are not computed independently and then concatenated channel-wise. It's one single step.
So X, Y, width and height, this is for the bounding box that is being set.
Yeah.
Like, okay, how was it trained? Like, how was the bounding box trained? Because there are,
So this was
like, how
trained.
to find, but because even though the regions that are we are selecting are like not pixel level, they are like big regions, not pixel level. But the bounding boxes have like pixel level differences as
Where? In this?
well. Like, not all the boxes
So,
are.
okay, if you look at this region here, there would be a bounding box that this predicts, there's a bounding box that this predicts, there's a bounding box that this predicts, and the number of candidate proposals is also tunable. So you can ask for 5 bounding boxes per grid cell. And this is something that he did in, I think, YOLO V3, where he was looking at different scales for the same cell. It would, so initially you just predict a bunch of bounding boxes just without knowing anything. And then once you compare that with your, once you score it using your intersection over union for localization, you're able to refine.
Like, I will predict, even if the region is saying something, I'll also predict bunch of bounding box and try to find the IUU and minimize.
Yeah, yeah. So it,
Like, the first step would be like there would be a bounding box around the side bicycle region, but still it would say it might be car and the error would be high. And then after training the model, the bounding box would be able to like.
think of it as if there's a network that has 3 branches that are doing 3 separate things. There's class probability prediction, which is one branch. There's bounding box prediction, which is another branch. And there's presence of an object probability, which is a third branch. Like conceptually, there's 3 things happening in parallel, and you're optimizing all 3 of those simultaneously using a 3-part loss function. But since prediction has to be in one step, all of that information is put together in this sort of a tensor.
Space, like, if there are more objects, the error would be higher.
Yes, because when you add all of it together, there's more terms. Uh, I mean, in that case, if that's your ultimate goal of just shooting for more object density in your data set, then you would probably split your data set according to density and do it iteratively, where you start on some reasonable amount of objects, and then once it's able to do that well, then you expose it to the denser ones. That's how I would try to do it anyway, rather than trying to. I mean, that's the simpler way to deal with it, unless it's a problem that's so hard that it um, is a constraint of the architecture itself. Um, in which case, you'd have to think about what changes to make. It it takes a while to sort of wrap your head around how everything can happen in one step, because we're used to thinking about doing things sequentially and then learning very defined uh, objectives to optimize for. But when you put all of them together, how that optimization happens jointly is um, hard to visualize, but it works. So it, it will that you'll have a moment when it all like falls into place and it makes sense. If you I really recommend reading all the YOLO papers, and they're written in a pretty accessible way. His his papers are famous for not following convention very strictly. Let me put it like that. Like if you look at some of his charts and the language that he writes with, it's very informal, which I think helps in his case. But he wouldn't have been able to get away with it if his results weren't as good as they are. Uh, yeah. Yeah. Yes. Questions?
Actually, in the feedback, you said like, never discuss our flow chart.
Right. Yeah. Yeah. Let me find that 1 second. Um, I'll put it up there once I find it. Close that. Um, What is your project about again? Just
It's about food. Yeah,
oh, right. Yeah. Yeah. Okay. Yeah. It's nothing. I don't have a problem with what you said necessarily. Just I think the sequence of things.
I wrote it down. First, first we're gonna do the molecular depth estimation and find out the depth maps.
I think it'll be faster if I can just find your original, because I remember what that one looked like. Uh, okay, that was refined proposal. Oh, there's two of.
Submitted same thing twice.
Okay. Um, Okay, so over here, you have your input pre-processing, object detection, food recognition, um, and then depth map, stereo, volume. So object detection is not going to give you depth
No,
maps. If you're,
I need to generate depth maps from the input images, right?
yeah, I mean, see, in your blocks, if you're putting like data artifacts, then keep that consistent throughout and put the algorithm along the arrows. So, or do it the other way around where you put the algorithm in. So you have an input image pre-processing. What does that do? That should be clear along your arrows because I don't know what data pre-processing is doing in this point. Object detection gives you classes and location, which you use to recognize food. Um, Object detection and depth maps, how do you get from there to there? That's not clear. So why depth estimation should be a step here of which the output would be depth maps. Stereo images, yeah, so depth maps, this would branch out before going into object detection. Stereo images and depth maps would give the same information, so I think they should also be parallel rather than sequential. Because you don't need depth maps to estimate stereo images, right? You need,
We need, right? Like, because we need the distance between camera and the particular thing, right? In order to get the disparity map, we need depth map.
I mean, the depth map is a disparity map between when you're doing it in stereo.
Like, I need to calculate the stereo images. Like, I don't have any stereo image right now.
Okay, okay.
From image,
So you're missing your,
using image and depth map, I need to calculate the stereo images.
okay, so how I would rephrase, let's see, I'm not going to, okay, just, but you have your input, which is an image. This, again, ideally, if you're able to like represent it like that, this is a batch of images, give height, width,
Yeah.
those sort of things. This goes into whatever your pre-processing block does. So whatever that is, then the output from that, then that goes into object detection, which gives bounding boxes, and that tells you location and class. So this you use for the like food material side of it. After that, whatever your pre-processed image is, that goes into monocular depth estimation, which gives you a depth map. Then you use this along with your original input, fuse that channel wise to predict missing side of stereo pair. Then you use your original input along with this to predict your 3D volume. Then you use this along with this information to estimate your calorie.
Got it. Yeah. Got it. Understood.
Yeah, if you're like the reason I ask you to come and just go over it with me is so that I also know that your understanding of what you're trying to build is clear. If Because if it's not, then you'll just get
Actually,
stuck.
we didn't convey it properly here. So
Yeah,
we
we
had a
are-
same thing which
We are actually doing the
But we
same
didn't
thing, but we
get a-
didn't convey it properly here.
Okay, yeah, fine. Yes. Who?
Yes, as Yoda, you suggested that we start channel wise, right? The class probability for objective.
The stacking part I'm also not very clear about. I'll have to read.
But okay, let's say for instance segmentation, how do you
Mm.
start class? Like there can be any number of instances.
The stacking of that tensor, how it's done, that's the key part. Because from what I understand, you can have a lot of those. Each of those is a self-contained output that is being predicted. Now, whether that is the question is whether that contains only one bounding box or whether it contains all of them. If it contains all of them, then there's no need to be stacking them. So I'll have to read up on that. I'm not
Because
very
there
clear.
are any number of, let's say for instance, there can be different cases for different inputs. Right? There can be output can have any number of instances.
Right.
So
Yeah.
it won't be standard while writing a model. How do we define our output?
I'll check and get back to you. Oh, that should be one of the things that gets covered organically as part of the walkthrough that I'm
Yeah,
trying to do for Tuesday. So in the process of doing that, I'll also figure it out.
Because the project we are working on, the cloud computing, if I want to segment it, cloud counting.
Mm.
So if I want to segment it, I don't know how to stack up the marks because there are a lot of head labels. Like there are like 2,000 head counts in a single image.
Mm.
But if I don't, if I can't do a segmentation, so right now I'm planning to do a density magnification.
Mm.
So with that, I can count the number of hits. I just want to know how to construct an instance segmentation.
Okay, yeah, I'll keep that in mind. Yeah.
So I just saw the project report 2 points.
Uh-huh.
How is that calculated for the n percentage?
Weightage,
Yeah.
it's
I
it's
wanna
not
consider-
going to be a major. See your final report, your video demo, and your how you present that is going to be majority of it. So a 95, 98, 100, that's all. Once I apply the weightage for it, it's going to be pretty much the same.
So you're gonna add all of the report 1, report 2, proposal.
Proposal, the first one, I'm not going to consider the score for that. Only the refined one and first update onwards. And even for that, those are going to have much less contribution than the final one. The scores are just to sort of give you a sense of whether it was perfect or whether there is room for improvement. That's all.
Actually, I got 98 out of 100.
Yeah, I gave only like 2 or 3 people 98. Majority, I think it was 95. And I don't remember if I gave anyone 100 or not.
I just followed the same, all the instructions you have given here. And I saw the comment as not including any visualizations.
See, even if this, it's not going to be more than 10% of the project component, each report. So if it is 10%, then that's what, a 9.8. And that again is part of only, what is it, 40% the project. So by the time you get to the final score, the 3 points here is not going to change things a whole lot. My goal is not to give you guys a hard time or a shitty grade. I just um,
No, I just don't want to make the same mistake in the next report coming up.
there's what feedback did I give you specifically? I must have mentioned something.
Yeah, about the vision.
Yeah, so
Yeah.
you saw how I was how I broke down the problem for the couple of people earlier. So just like that, because it's a multi-step problem where um, you also want to draw parallels with what we're doing in class, which is like at one step you have feature maps, or next step you have locations, or that is a good way to get across the entirety of a project in just one image, right? So then I know what to look for in your descriptive explanation. Without that, then the way everyone thinks about their project, the sequence in which they talk about it, and the level of abstraction and detail varies a lot from person to person. So this gives me a uniform format that I can parse at a glance. And that, like, generally, if you come across any paper that does anything vision based, you would expect to see some sort of visual representation of what's going on, right? I know that's not something that I explicitly asked for as a rubric or whatever, but which is also why I didn't like cut 20, 30, whatever points. It's just 5 points that I'm cutting. Do you have a question or just waiting? Okay.